Let's continue our discussion about Maxwell equation in differential form. On last Thursday, we looked into the problem about example 3.1, which gives you an expression for the electrical field. It's a time-varying electrical field. And in fact, it's a time-varying electrical wave propagating in the positive z direction. So according to the expression for the electrical field, which is in the form of a constant value E sub 0, which is the magnitude of the maximum magnitude of the electrical field, times cosine omega t minus beta z in this general form. The omega specifies the frequency dependence of the signal, which omega is referred to as the angular frequency, and it's equivalent to 2 pi times frequency f. And beta is referred as the wave number, which is associated to the wavelength of the electromagnetic wave. And in the parameters of the cosine function, here is the dependence on z, which tells you that the electrical field varies can be different at a different position. This also suggests that the electromagnetic wave is propagated in the z direction. In particular, it's going into the positive z direction as t increases. So as the time progresses, the electromagnetic wave, the field, and the wave and its field is moving toward the positive z direction. So according to the relationship, that is the time derivative of magnetic flux density, By, the time derivative of magnetic flux density, By, equals to the special derivative toward the z direction of Ex. Yeah, I dropped the direction of the electrical field. And so the problem asks you to find out the expression for B, the magnetic flux density. And we can use this relationship to find out B from the expression of E. That is, you need to first do the special derivative, to find the special derivative of Ex toward the z direction, that is differentiated with respect to z, then integrate the expression in terms of t to find out the Bz components, By components of the magnetic flux density. So once you understand the process, the result is quite straightforward. So we first differentiate the expression for E toward the z direction. And as you can see in this cosine function, if you want to do the differentiation toward z, you will drop minus 2 pi to the front. So it becomes minus 20 pi. And the cosine function is changed into sine function, as you can see here. And taking into account the minus sign in front of the special derivative, so you need to be careful about the sign of this expression. So this is the special derivative of Ex toward the z direction, and taking the negative of it. And then you integrate it with respect to t. So you will transform it from sine function back to cosine function with the addition of the angular frequency, omega, which equals to 6 pi times 10 to the 8th. So the result of this time domain integration becomes 10 to the minus 7 over 3 divided times cosine omega t minus 2 pi z. Omega t minus 2 pi z as shown here. So be sure to practice this process yourself, okay? And next, let's try to derive the general form for the differential equation of the Faraday's law. That is, the electrical field has components in all, has projection in all directions, including Ex, Ey, and Ez. So the Faraday's law in the integral form, that is the closed loop integral of E equals to the minus of the time derivative of flux of the surface integral of magnetic flux density, can be transformed into a problem like this. So you have three regions, including the xy plane, yz plane, and the xz plane. So in each plane, you can write up a relationship about the closed loop integral of the electrical field intensity. And for example, if you check up the plane formed by nodes of A, B, C, D. So the A, B, C, D, A pass loop, which lies on the YZ plane, can be written as can be divided into 4 line integral, which includes EY in the Y direction, EZ in the Z direction, and the 2. So when you look at equation 3.9a, try to check up the expression to the right and the illustration to the left. So here, first let's look at the blue arrow to the right, that is the first integral. So it's this performs the line integral from point A to point B, and because the line is pointing to the y direction, so only the EY components count in this differential length. In this differential length. So the line integral of this path becomes EY times delta y. And we use the EY value at the beginning point. We do not track every point, the variation of electrical field at every point. Why? Because we are checking a very, very small region. It's so small that you can think of the electrical field on this path is almost uniform. So the line integral can be simplified or can be reduced into the product of the length delta y and the average field intensity EY as shown here. So the second line integral, that is from B to C, is the second term over here. So here you check, you found you only account for the EZ component because this path is oriented in the positive Z direction. And the third term is this smaller blue arrow pointing to the left, so you see the electrical field expression is expressed at the point, the observation point is a little bit different toward the first one. Its location becomes z plus delta z, which is located a slightly higher position. And the first term will be the red arrow pointing to the bottom. So you see the first two terms are positive, positive, then the third and fourth terms are negative and negative. Why? Because the path direction are different in this path pairs. So this one is going to the right, this one is going to the left, this one is pointing upward, and this one is pointing downward. So you have the minus sign here. And you can do the same for the other two closed square loops, which are on the zx plane and the xy plane. And these are the this law in integral form to the left, which are the closed loop integral of electrical field intensity. And for this law in the integral form, to the right is the surface integral of the magnetic flux accumulated in a specific area. That is the surface integral of magnetic flux density B over a specific region. So it can also be decomposed in two regions on the YZ plane, XZ plane, and XY plane, and you only account for, because the region is so small, it can be simplified as the represented magnetic flux density at a specific point or in an average sense. So it becomes Bx times delta y delta z. So the latter two is the surface area that we are interested, and the first term, the Bx, is the average magnetic flux density in this small region. So you have three expressions which accounts for the magnetic flux passing through the YZ plane, the XZ plane, and the XY plane. And next, we can combine the left-hand side and right-hand side of the Faraday's law as in this format. Okay? So here, in fact, the delta y, delta z are originally placed on the right-hand side. And the delta t is placed, So you divided both sides with delta y and delta z. And it becomes, for each equations, this accounts for the EZ component difference with respect to delta y on the y direction. The second term evaluates the difference of EY in which direction? In the z direction. And to the right of the equation is the time derivative of Bx. And you can also find relationship on other planes. This one is for the YZ plane, this one is for the XZ plane, and the third one is for the XY plane. And the expression here, the three expression here, can be put into a simpler form as this, as equation 3.12a, b, and c. So the first term is reduced as del Ez over del y. So which means you evaluate the difference of Ez on the direction on the y direction. The second term is evaluate the difference in EY on the z direction. And the third term, that is to the right, is to evaluate the difference of Bx as the time changes. So have you noticed that in every turn to the left, the difference in electrical field intensity are evaluated on a direction that is transverse to the field itself. So here is EZ over Y, EY over Z, EX over Z, EZ over X. So it's evaluate the difference on a direction that is orthogonal to the field direction. This kind of evaluation is referred to as lateral difference. This kind of evaluation is referred to as lateral difference or lateral differentiation. So this is the E direction. And the so-called lateral differentiation is you check if the field, the E field on its side is the same or not. If, in this case, you can see the E field has lateral derivatives. That is, the electrical field intensity that is parallel to its own to the observation direction as a little bit or somewhat different to this one. On the other hand, for this case, if the phi field are the same on its lateral direction, on its side, it will have no lateral derivative. 所以这边你看到的空间微分，它强调的是跟它侧边的场做比较，不是顺着那个场的方向，不是哦，它是强调的是往侧边的场之间有没有变动，有没有区别，那原因是这一种的空间微分，这种的空间微分我们称之为 curve operation。我们等一下会再看到了称之为 curve operation。curve operation 的话，你可以说它是观察 lateral direction， 这侧边方向有没有不一样。那你也看到从这个符号只有在第三章你看到倒三角，它代表的就是什么？空间的微分。倒三角就是空间的微分。在这一本电磁学里头，在电磁学里头你会看到好多种倒三角。那个倒三角就表示是空间的微分，但空间微分有很多种，它有 curve operation、divergence operation， 这个是对于向量场的有 curve operation、divergence operation， 对存量场有所谓的 gradient operation，gradient 梯度旋度、闪度、梯度，然后我们还会看到后面一点还会看到二次的偏微分叫拉普拉斯。或者是二次的，这是二次的存量偏微分，还有二次的向量偏微分，所以也叫拉普拉斯。所以拉普拉斯的 Laplacian operation 还分作向量的 Laplacian， 还有存量的 Laplacian。搞死你啊 ！OK 对啊，就我们慢慢认识他们吧。Alright, so. As you can see here, as you can see on the remarks on this slide, the first equation evaluates the time derivative, time difference of bx and it's associated with the difference of EZ in the y direction and the difference of EY in the z direction. For the second term, it evaluates EX and EZ differentiation on the lateral direction. So they can be associated to each other. And in this slide, so here, this result suggests that the time domain difference of the magnetic field is associated with the spatial difference of the electrical field. So the space variation of electrical field is associated, is related to the time domain variation of the magnetic field, actually, and vice versa. And in particular, we know that the space derivatives are all lateral derivative, as I already mentioned. That is the difference toward the field, the side of the fields, the side of the field. And here is, in this slide, it's notify you to be careful about the order, of the spatial derivative. For example, this one's, if you look, it's EZ over del y. So as the y is pointing to the right, you see the EZ becomes larger and larger. So the first term will give you a positive number. And the second term, that is del EY over del Z, del EY over del Z, that is evaluate the difference of EY toward the Z direction, and it's also a positive number because, as you can see here, is the EY value the magnitude of EY becomes larger. However, because the two terms are connected with a minus sign, so the result of this field variation may end up with a 0. Now, on the other hand, for this case, for the B case, EZ is larger to the right and EY is smaller to the positive Z direction. So the first term is a positive number and the second term is a negative number, and because they are related with a minus relationship, so you will end up with a positive number for this kind of field variation. So that's something you can be aware of. All right. And the three relationships, as we observed in the equations 3.12a, b, and c, which are associated with the time domain variation of b on the x direction, y direction, and z direction. So those three equations can be collected to form equation 3.13. So that write up this differentiation in terms of vectors, or in the vectors form. So to the right are time derivative of B of the magnetic flux density B toward x in x direction, y direction, and z direction. And the left-hand side of equation 3.12 can also be collected as result in the x direction, y direction, and z direction. So again, check out this term. You see, for the x components, the x component is associated with EZ differences on the y direction, EY differences in the z direction, and this result is placed in the x direction. Now, so they are all in the lateral direction. They are, in fact, exhibit in the cross form, cross product form. So the equations 3.13 can be memorized more easily as equation 3.14. All right? This is not an I would say this is not an official format for equation 3.13, but it's make you easier to remember and easier to operate. So to be sure to remember this form, this is referred to as the determinant form. 中文叫什么？我忘记了 determinant form 了哈。All right, and this can be put more easily as this equation 3.15, which in the next slide you will see the official expression for this law in differential form. That is the curve of electrical field intensity equals to the minus of the time derivative of magnetic flux density. Okay. So this is the spatial derivative. Remember the del sign. Okay, this is not. 知道哈，这是 delta 哈，这是 del 哈。所以 del sign means spatial derivative 空间的微分 is you are trying to find out the difference in the x direction. You try to find out the difference of in terms of x in the x direction, the difference toward y in the y direction, difference of z in the z direction. And this is performed in the curve operation is performed in the cross form, 外积的形式. And this term is the field vectors to be differentiated, and they are associated with the minus of the time derivative of magnetic flux density. All right, so equation 3.17 is the Maxwell equation in differential form corresponding to Faraday's law, 法拉第定律的微分形式，请把它记下来。Okay, and it tells us that for a point in the space, the electromagnetic field, the relationship of its magnetic field, the curve of the electrical field intensity equals to the time rate of decrease of the magnetic flux density. So this is the verbal expression for the Faraday's law in differential form. So for differential Maxwell equations, we are always interested, or we always concerned about the field relationship at a specific point. 所以积分形式，第二章中讲的积分形式的 Maxwell equation 是对一个区域的场跟两种场电场跟磁场的时空变化有关系去做描述，去找出它们的关系。但在第三章中的微分形式，则是对一个点，对空间中的一个点，它的电场、磁场的时变空间变化关系去做描述。所以积分形式跟微分形式，当然在表现上面是不一样的，关系数学式上面看起来是不一样的，但是在我们这几堂上课的时候，我们在推导微分形式的 Maxwell equation 的时候，也让你看到我们把积分形式的 Maxwell equation 的所感到，你知道积分形式是一个区域嘛？当你把那个区域缩到很小很小很小的时候，就给你微分形式了，给你微分形式。所以它们两者之间是可以有关系，可以找到它们之间的关系的。Alright, so according to equation 3.17, it shows that if we are interested in a static field, so suppose you tell me that the electric and magnetic field in this position, in this region, is static field, which means they have no time derivative, then you will end up as the curl of E equals to what? Equals to 0. Because when you are only interested, or when you are attempts to describe the relationship of static field, then the electric and magnetic fields are decoupled. If there is no time derivative for the magnetic field, then the curl of E shall equals to 0. The lateral derivatives of electrical field, that is, the electrical fields, the differences of the electrical field on its sides has no difference. No, the lateral derivatives are 0. Okay, and of course we begin our discussion about curl operation in the Cartesian form, which is relatively simple. Okay, and here we will see the curl operation in cylindrical coordinate system and spherical coordinate system. And 20分呢？好，20分这个，基本上送分了OK 好，所以一定会考的那我当然不会考你直角坐标系统的旋度操作或闪度操作嘛，对不对？那会给，不用担心会有，不用记啦，但是要稍微留个印象吧。比如让你在 cylindrical coordinate system 里头，你的那个上面这边是前面这两个都有 r 分之一，那这边多了一个 r，多了一个 r， 所以你在操作的时候注意这个 r 是要拿进去一起做微分的。这个 r 呢是不参与微分的操作，它是摆在外面的 ，OK 所以练习题要做啦 ，homework 要做 ，homework 里头应该有这一个的那个的练习题啦那在球坐标系统的话，这一个要摆上去的修正项就比较多，比较复杂一点对。我每次考试起码都会有40分到50分是送分的嘛，对不对？那当然你都不做考古题，也不做 homework， 那你也没有收到，我就没办法了OK Alright, so here is a products for the curl operation. So it's we have the example 3.2 asks you to find out the curls of the first one is vector in the Cartesian coordinate system. So you write up the operation in the determinant form. So to be sure to use the determinant form, which is easier to remember, and follow the through of the calculation of determinants. You can perform the derivative. Say this one, this is finding the derivative of the function minus x towards z, and because the minus x function has no z dependence, so this ends up to 0, and this one ends up to 0 as well. And this one you have the relationship of -1, -1, because the first term is -1, the second term is 1, so you end up with -2 in the z direction. So be sure to practice by yourself. The second question of example 3.2 is finding the constant, the curl of a constant in the phi direction. And it turns out the operation result of this thing is 1 over r. 1 over r. So to be sure that you know how to derive this solution 这自己要练习一下，好不好 All right, so next we can find out the ampere sequential law in the differential form 安培电路定理的微分形式。那我们也不用从头再推导一次了，我们可以用比较的方式把它拿来我们先比较一下积分形式的安培电路定理跟法拉第定理，然后再来去猜一猜微分形式的安培电路定理应该长什么样子因为我们刚刚已经推出微分形式的法拉第定理了OK， so you see to the bottom left is the comparison of Faraday's law in integral form and the differential form. So the closed loop integral of electrical field becomes curl operation of E. And the time derivative of magnetic flux, which is the total magnetic flux in a region. When the region is reduced to a point, then we no longer need the surface integral. We only interested about the magnetic flux density on a specific point. So the surface integral can be dropped, and it becomes, look at the time derivative of B, and this is associated to the curl of E in this observation point. So this is the relationship between integral and differential form of Faraday's law. So as you can see, to the left is the ampere sequential law in integral form. So by analogy of the Faraday's law, we can write up the ampere sequential form in differential format, ampere sequential law in differential format. So to the left of the equation is, this is the closed loop integral of H, so it's written as the curl of H at a specific point. And to the right, which are surface integral of electrical current density and time derivative of displacement flux. And as according to the analogy of the Faraday's law, we know that the the surface integral can be dropped. So it's reduced to J, the electrical current density, and the time derivative of electrical displacement flux density D at that point. So equation 3.21 is the Faraday's law in ampere sequential form. So they are not difficult to remember, right? And with this analogy, it can be found quite somewhat symmetric for the Faraday's law and ampere sequential law. All right? So in Cartesian coordinate system, the equation 3.21 can be expressed as equation 3.22 like this, in determinant form, which is easier to operate. So you can remember that to find out this, you first do the special derivative of hz in the right toward y minus hy derivative toward z, and the result is in the x component, like something like that. And let's consider a particular case, a special case for h that fully relies on the y direction, so it's returned as hy, which is a function of time and the space, that is the z direction. Now, so h does not have dependency on x and y direction, so the spatial derivative of h toward x and y are all zeros. So if you perform the determinant for differentiation, you end up like this. So you have something like that. So what is the implication of this result? It tells you that the hy variation toward the z direction equals to currents in the x direction. So for curl operator, for curl operator， 这边请你要回去看一下想清楚也就是说，我觉得电场跟电荷的关系比较容易记，因为电荷所产生的电场就是顺着电荷往外散出的方向，所以电荷跟电场的关系比较容易记，但电流跟磁场的关系，也就是安培右手定则，它会比较不是那么的直觉啦，有一点反直觉啦，所以你会看到像这个式子为什么要你多看几遍，就会看到说电流是在 x 方向，但电流跟谁有关系呢？跟 y 方向的磁场在 z 方向的变化。y 方向的磁场在 z 方向的变化。事实上还有一个比较完整的，这个东西比较完整的写起来应该是，假如你从这边过来的话，你会看到的是 minus jx minus time derivative of x shall equal to是这两个所以 hy 在 z 方向的变动跟 hz 在 y 方向的变动都会扯到 x 方向的电流变动所以这整个是在 ax 方向上所以这个 curl operation反度的关系它的那个方向上的关系你要多留意一下 OK and here is example 3.3 so in this example the problem provides you an electrical field intensity expression and you are asked to verify whether or not this electrical field is a legit electrical field, which means it belongs to our propagating waves, propagating electromagnetic wave. 所以 example 3.3 要问你的是这样子一个电场描述，这边你可以看得出来它是一个电场描述啊，为什么？因为这个电场描述有空间的描述，比如说 z。它是落在 x 方向，然后它会随着位置 z 而改变。它有时间的描述，它的时间的变动是 exponential minus t。所以这个电场它有时间的描述，有空间的描述，但是它是电磁波吗？它是不是一个合法或者说合理的电磁场？这个就不一定了。那解决的方法或者是证明的方法就是，我们把刚刚的安培电路定理跟法拉第定理拿来用一下也就是说这个是 EX 嘛，所以 EX 对 Z 的微分应该可以相当于 BY 对时间的微分，所以你把它先微再积你就可以得到它的磁场的表示式，然后把这个磁场呢再带到，把这个磁场的表示式再带到安培电路定理把磁场对 z 微分呢，然后再对时间积分呢，又可以得到 dx 的表示式，而 dx 跟 E 呢又只差一个 epsilon 而已所以你又可以回到 电场的表示式。所以你把这一个 EX 呢，透过法拉利定律跟安培电路定律去检视一下你可以再找，理论上你应该再得回到它的电场表示式。但这一个 example 给你的状况是，你只要 follow 这个 ，if you follow the procedural description about Faraday's law and Ampere-Circuit law, you end up with this relationship. That is, again, is an electrical field intensity on the x direction. On the x direction, it becomes 2 times E sub 0 times exponential minus t. You see, and compare this result with the original expression for the electrical field. Are they the same? No. In this one, you have z to the square, and here you don't have z dependence, and you end up with the 1 over mu sub 0 and epsilon sub 0. So they are not the same, and this implies that this expression for the electrical field is not a legit expression for electromagnetic wave, because it does not satisfy the Faraday's law and Ampere-Circuit law simultaneously. 它没有办法同时满足法拉利定律跟安培电路定律所以我们可以说它不是一个合法合理的一个电场表示式，它不能够说它是一个合法合理的电磁波吧所以它电磁波的电磁场不会是这个样子。Okay, so the very last part of section 3.1 discuss a little bit about the relationship of electromagnetics and electric circuits. 电路学跟电磁学的关系啦From the perspective of electromagnetics, we can say that electric circuit theory is only a special case of the electromagnetics. And it's specialized, the electric circuit theory specialized at the low frequency behavior of electromagnetic fields. And it makes some assumption that the electrical circuit theory is developed under the assumption that the frequency is small, so that some of the relationship we observe in the Maxwell equation are neglected. For example, if you look at the relationship of an inductor, it taking into account of time-varying magnetic field, but it ignores the effect of time-varying electrical field. 所以对电感来讲，它有计入到时变磁场的影响。因为这里头你看这个电感式子里头，你有 I 对时间的微分，所以事实上它有考虑到时变磁场的影响。在电容表示式里头，你有考虑到这个是电容表示式嘛？你有考虑到时变电压的影响，所以它有考虑到时变电场的影响，但是它没有考虑到时变磁场。所以电路学的关系式，其实你从电磁学的角度来讲，电路学的关系式是不完整的，它是一个低频的趋近，它是一个 special case 那像更明显的是电阻关系式V equals to R times I. You see, there is no dependence about time-varying electrical field and time-varying electrical field. Nevertheless, from the history perspective, the Maxwell equation or electromagnetics is actually developed under the basis of electrical circuit theory 但在历史上来讲，其实电磁学是站在电路学的基础上面发展出来的虽然说你回顾它以现在的角度来看，你就说电路学只是电磁学的一个 special case 但是其实 我们现在在学的电磁学或者说微波电路的理论，其实都是从电路学的基础上面发展出来的And as to the description of electromagnetic waves, the both time derivative terms, including the magnetic one and the electrical one, cannot be neglected. So we have, 所以我们讲说磁生电、电生磁的话，你只要导出电磁波呢，这两项就都不可以忽略。OK， 好，那我们今天就先到这边吧，